The object that you're looking at, why it looks a certain color is because all wavelengths of light that hit the surface, that are absorbed, whatever is reflected off of that object is the color that you see. So in this case, the apple is red. You see it as red because white light, which has all wavelengths of color, go and zap the apple, right? And most of the wavelengths are absorbed except for red. So our eyes detect these red light waves, and your mind reads the light as being a certain color. How does that happen? Light enters your eye and travels to a membrane of nerve tissue called the retina at the back of your eyeball. So it's the back of your eyeball that detects color. Okay? And you have cells in this area that react to light. One type of cell receives impressions of lightness and darkness, and the other receives the color. Now, if you think about the absorption of light into whatever object it is, if you think about that in the way of temperature, like when you're wearing a black t-shirt in the summertime and you tend to get hot versus a white t-shirt, and there's a lot of debate around whether or not this is true, or if it's the fact that you're wearing really tight clothing or you're in a different climate, in a hotter climate, whatever. But basically, if you think about it like that, just as an example, a black t-shirt, the reason it's black is because it's absorbing all wavelengths of light and reflecting nothing. And a white t-shirt's reflecting everything. So the energy that's absorbed by the black t-shirt makes it warmer. So colors don't really change. Like the apple is always going to be red with light, of course. Light, it's not red in a dark room. But our ability to distinguish between colors does change. So when it's dim light, we can't see colors as well. Light will change whether or not the object has sunlight on it or a lamp light. And when you're looking at colors, because of all these factors, your eyes can sometimes fool you. This is an example of what your eye does when you're in a dark or bright room. So in dim light, your pupil dilates a lot because your eye is trying to get as much light as possible, trying to figure out what's going on. And then when something's really bright, your pupil gets really, really tiny because it's like, oh, too much light, and it can kind of contracts a little bit. So the parts of the eyeball here. When light hits an object, like a banana, the object absorbs some of that light and reflects the rest of it. The reflected light enters your eye first through the cornea, the outermost part, then it bends the light toward the pupil, which controls the amount of light, as we just said, that hits the lens. And then the lens focuses the light on the retina all the way in the back, the layer of the nerve cells that registers color. You have rods and cones in your eyes that respond to light. Rods are activated when you're in low or dim light, and cones are stimulated in brighter environments. So think about this later when we talk about night vision. Rods are affected by light at night. Cones contain photopigments, or color detecting molecules, and humans have 3 types of photopigments that detect color. There's red, green, and blue. Red, green, and blue cones. That's it. And they're sensitive to different wavelengths of visible light. Now, banana is yellow because a banana is reflecting a light that has both red and green cones. The in-between red and green is yellow, so our eye sees the banana. It's neither red or green, so the red and green cones are firing and activating. And what happens, because they're both activating those cones, it goes to the in-between the cones and says, oh, that object is yellow. In a darker environment, the light reflected by the banana would stimulate only the rods in your eyes. If only the rods are activated, you don't really see color, you just see shades of gray. And once light activates it more, then your cones are affected a little bit more, and then you start seeing the color. This is kind of a little exercise for you to show you how your cones work. I want you to stare at the red square for 30 seconds, and then when I say look to the right, then you look to the right in that blank white space. Okay? So 30 seconds, go ahead, stare at that red square. Don't move your eyes, just focus in. All right, go ahead and look quickly to the right. Did you see a green or a blue shape in the white area? That's called an after image. So because your red cones were so tired from looking at the red, overloaded by it, just overloaded. Your eyes reverted to the blue and green cones as like, oh, I need a break. There are these other cones. That's what happened, creating that after image for you. Now, some artists use this kind of concept of how our eyes work with different colors and can be fatigued for their advantage to make really interesting art. This is a Larry Poons painting called Orange Crush. Do the same thing. 1963 is the date. Do the same thing and stare at this for 30 seconds and then look quickly to the right. All right, go ahead. All right, look to the right. Did everyone see kind of the dots in the white space when they looked over? That's just another example of how your cones are kind of overexerted. Now talking about wavelengths. So blue wavelengths of light are shorter in distance. So there's more of them. So they're more energetic. Blue light, it energizes you for sure. Blue light comes in our screens, in our computers, television, phones, LED lights. But they're not good after a certain time, like when you want to go to bed, or even 2 hours before you go to bed. So if you are not having a great night's sleep, or you haven't had a great night's sleep for a couple weeks or something, it's probably because you've been on your phone or your computer right before you went to bed. So the best idea would be to not look at any blue wavelengths of light a couple hours before you go to bed. Red light, who would have thought red light would be the best light for us? If we think about the color red, it's has such powerful associations about passion, aggression, anger, and fear, and then all of a sudden it's like, no, red light's the best, it's the nicest. It is, it's the nicest light for you to absorb. Because the wavelength of red light is longer and it's easier to handle. Obviously not when you're staring at red color pigment like we did in the exercise, but the red light itself. Red light is different than red color. But anyway, get yourself a red lamp if you feel like you need some more sleep, or just look at red light before you go to bed. That's why, the taillights of your cars are red, because at night you don't want to disrupt the rods in your eyes. The rods are the part of your eye that enables you to see in darkness and understand the lightness or darkness of something. So you need your rods at night. You don't really necessarily need your cones. So that's why red light does not mess your eyes up as much. That's why they're tail lights. That's why we used to use them. I worked in a hiking program, and we would put red lights out on the path for people to continue to follow the path and not get lost. So as soon as you put a flashlight in someone's face at night, it activates the cones all of a sudden. And then when you turn the flashlight off, you can't see that much for a little bit, and then you'll have to adjust your eyes. Your eyes will adjust again. So your night vision is better with just red light. Also, they did a little study at Ohio State University where a bunch of US neuroscientists got together and did a study on the health hazards of light at night. And they looked at the effects of a range of different colored lights on hamsters, who are hamsters or not. Results showed that blue light, the kind emitted by electronics and energy efficient light bulbs, had the worst effects on rodents' moods, followed closely by white light. Hamsters exposed to red light at night fared much better. They had significantly less depression-like symptoms and changes in the brain linked to depression. And they slept better. They did more. They went to their jobs in the morning happier. And the only rodents that fared best of all were the ones who spent the night in total darkness. So what that really tells us is we should really revert back to our pre-electricity lives. We should go to bed when the sun goes down. The sun is our natural light. As soon as it goes down, go to sleep. All right, we're going to talk about additive color versus subtractive color because this can get confusing, and it still remains confusing to me a little bit. But you need to know about it because it's in the world around us, and it affects our ideas and perceptions of color. Additive color is about light. Subtractive color is pigment. We will be working with subtractive color, but additive color, what we just talked about with light and seeing objects, that is color light. Okay. Red, green, and blue, like the cones in your eyes. Red, green, blue. It's produced with light, not paint. Televisions, computer monitors, phones, screens, all use the knowledge of how your eye works with the cones of red, green, and blue to create all other colors on the screen. It's a little trick. So it's hard to explain without seeing it in person in a dark room, but we'll just pretend you're in a dark room, and these are the lights that are shining on the wall. A blue light, a green light, and a red light. All connected for a reason, because when red and blue light are connected, the intersection gives you magenta. When red and green connect, you get yellow, and when blue and green connect, you get cyan, which are magenta, cyan, and yellow are primary colors for the CMYK color system. Don't get too confused. All those lights together make white light. So all white light has these colors in them, okay? This is called additive because we begin in total darkness. We got nothing, and then we add on to the blackness. As we add more colored light, red, then blue, then yellow, it gets lighter and lighter and lighter, 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 until it's white light. This is how digital technology works. All colors are created from a various combination of pixels that are red, green, and blue. When you're in Photoshop or Illustrator, it's going to ask you what mode you want to work in, RGB or CMYK. That's what it means. RGB is about light. If you are working in those programs and you are planning to show your artwork on a screen, you need to make sure that you're in RGB mode. If you're working in those programs and you are going to print something out, you need to be in CMYK, which is what we're going to talk about next. But that just means, say you have a drawing and you take a picture of it or you scan it into the program and you want to create a portfolio that you present, you should make those images RGB so that they look the best. They will not look the same if they're in the wrong mode. Just a little side note to anyone who's getting into graphic design. So these are the pixels. If you were to zoom in on your television, this is what you would see. Green, blue, red pixels, a lot of them. And what they do and we're not going to get into this too much, but as you can imagine, a combination of these in the television kind of magically goes to your eyeball, and different combinations create different colors that you perceive to be different colors. Can you imagine what it was like to actually see color television for the first time? That must have been interesting. If we were designing a poster or something to be printed, you'd be in CMYK. CMYK has to do with pigments of ink. If you have a printer at home and you go and you buy yourself some ink, you will buy a cartridge. The color cartridge will come with CMY. And you'll already have a black, which will combine together. Black will be part of the printer. What does K stand for? Black. Kind of gave it away. Why? K means key in that world. K is key. The print, when you're printing something, and you can even see this in a newspaper, an old school newspaper, the color images, if you zoom real close, you'll be able to see the layers of dots on top of each other. What's happening in the printed page is this is subtractive color. It's doing the opposite of the additive. Final CMYK, you got your layers of cyan, magenta, yellow, and black on top of each other. And this is a detailed view of what you can see. This is what you do in screen printing when you are printing a photo. You'll divide the photo up into layers of CMYK, and then you'll print them. Print the cyan, you'll print the magenta, the yellow, and the black all on top of each other, and then voila, you have a color print. So we're not going to think about the digital part of color right now, but we're going to kind of tie it into how we paint and think about how we are doing our painting. So our eyes are the monitor and our hands are the printer now. We're going to mix the ink and lay it down when our eyes translate what we see. This process is called subtractive because you begin with white, and as more colors are added, the results get darker and darker until it turns black. So that's why it's not additive. Additive, that system was with light, and it was a dark room. You start with black, and then you add light, light, light until it turns white. This is subtractive because you have white, and then you add on color until it becomes black, or whatever darkest color that you achieve. This is why, the reason why you, at some point, your colors when you mix get too dark and you can't make them brighter by adding white. Like, it's impossible. It just becomes muddier and gross. Keep that in mind when you're mixing, that if it is super dark, it's impossible to brighten it up, especially with white.